All right. So here's the question. All right. So we have this diagram here, and it says a uniform square lamina of side 2A and weight W is suspended from a light inextensible string attached to the midpoint E of the side AB. The other end of the string is attached to a fixed point P on a rough vertical wall. The vertex B of the lamina is in contact with the wall, and the string EP is perpendicular to the side AB and makes an angle theta with the wall as seen on the diagram. The string and the lamina are in a vertical plane perpendicular to the wall, and the coefficient of friction between the wall and the lamina is a half. Given that the vertex B is about to slip up the wall, find the value of tan theta. All right, so we're going to start by taking into account all the forces that are at play. All right. So the forces at play in this particular situation, we can start with the string EP because from the question, they tell us that this square lamina has been suspended from a light inextensible string attached to the midpoint E of the side AB. So there has to be tension in the string. So that is the first force. The second important force at play is the weight of the lamina, all right? And it has to act from the geometrical center of the lamina. So it's going vertically downwards. And we've been told that the weight is W here. So we have W here. Next, there's contact around here between the lamina and the vertical wall. So since there are contact forces here, we have to take into account the normal, okay? The normal reaction force, all right? So for the normal, we can call that R, okay? That's the normal reaction force at B, all right? Next, we have been given the information that the vertex B is about to slip up the wall. All right. And remember, it's a rough contact. And we also have the coefficient of friction being a half. So that's the other piece of information we have. So we know that mu is equal to a half, and the vertex B is about to slip up the wall. So if it is about to slip up the wall, it means friction will be acting against possible motion. So the frictional force, which I'm calling F here, should be acting downwards. All right. So what I have here, all right, are the forces at play. And we actually have in total four main forces that are at play in this particular situation. All right. So in solving problems like these, we have to consider a number of things. We are going to consider, firstly, the principle of moments, okay, where we are saying that the sum of moments about any point is equal to zero. So we're going to consider that, all right? And we're also going to consider the fact that the resultant force in any direction is also equal to zero. So we're also going to consider that. And why are we considering these two things? Is because we've been told in the question that this system is in equilibrium. So we actually have a system in equilibrium. And how do we know that the system is in equilibrium? Because we are at a point where the vertex B is about to slip at the wall. So it's more like limiting friction, limiting equilibrium type of thing going on. So because we are at limiting equilibrium, we also need to consider the third thing, that's at limiting equilibrium, F is equal to mu R. So these are the three main things that we're going to consider, considering that the system is in equilibrium. We're going to start with the first thing, the fact that the sum of moments about any point is equal to zero. And we're going to calculate moments about any point. We're going to let's make use of the point B. So let's do moments about the point B. So I'll say here, taking moments about B. All right. Let us consider the forces. All right. Let's start with the tensional force. Okay. This force T. The moment is the force T times its perpendicular distance to B. All right. And the perpendicular distance to B is actually A. So it's T times A. All right. So that's T times A that we got right here. And apparently, this is a clockwise moment that this force is going to cause. So that's clockwise. All right. We also have for the force W, which is the weight, which is going to cause, in this case, about B, an anti-clockwise moment. All right. So for the W force, we are going to consider, all right, its perpendicular distance from B, which can be a little bit tricky for us to find. But what we're going to do is we're going to consider the force W to be a resultant of two different forces. It is a resultant of two perpendicular forces. So we can have this component of W, all right, and this component of W, all right. And apparently, considering the fact that this little angle here is going to be theta, we can say for this particular component that it's in actual fact the component W cos of theta, and this other component is W sine of theta. So we're going to make use, because it's better for us to work with those components to find the moment for the force W. Okay, so let's start with the component W cos theta. All right, and W cos theta, its line of action is actually this line here. And the perpendicular distance of the line of action of W cos theta from B is again the distance A, if you can see that. So it's W cos theta times A. All right. But I'm going to put a different sign to it because it's anti-clockwise. Remember, this force was clockwise. So I'm going to say minus W cos theta times A. All right. Then for the other component of the W force, which is this one here, if you can look at its line of action, okay, the line of action of the force, you can actually see that its perpendicular distance from B is actually again half of 2A. It's again A. So the moment is W sine theta times A. All right. Again, it is going to cause an anticlockwise moment. So I'll use again a negative sign. So that's minus W sine theta times perpendicular distance is again A. Next, we're going to consider the force R. And the force R will have zero moment, okay? Zero moment about B because its perpendicular distance from B is technically zero, okay? And that's the same with the force F. So these are the forces that are at play, and we're going to say that the total moments is zero. All right. So technically, we have, if we rearrange, that's TA being equal to WA cos theta plus WA sine theta. I can actually see that we can say TA is equal to WA of cos theta plus sine theta if we factor out WA. And we can actually divide both sides by A so that we can have T being equal to W of cos theta plus sine of theta. So let's leave it here for now. Okay, I'm just going to call this equation 1 as we are likely going to need it along the way. So we have done the very first thing, and that is taking moments about B, okay, and using the fact that the sum of moments about any point is 0. Now we want to do the second important thing, which is to consider that the resultant force in any direction is 0. So let's consider that, okay? So that's going to be number 2, okay? So we are going to be resolving, and resolving, we have to resolve in two perpendicular directions. And the two perpendicular directions we're going to consider will be vertically and horizontally, essentially. Actually, the arrow should be going this way. So these are the two perpendicular directions we're going to be resolving in. Let's start with resolving vertically, all right? So we're going to start resolving vertically, all right? Now, we're going to consider all the forces that are going upwards, okay, or vertically rather. And I want you to consider here for the force T, if I draw its line of action, the force T in green, if you can see, it kind of goes actually in this direction. Then I can also draw a horizontal on it so that we have some kind of a right angle here. So essentially, the vertical component is this one here, which is T cos theta. So for the T force, it's T cos theta going upwards. Okay. Then, so we are done with the T force. Then W is going downwards, and so is F. So I would say minus W minus F, and there's no other force acting vertically. So we will say that this is equal to 0. Okay. And we can rearrange this so that we have W plus F being equal to T cos of theta. I'm just going to call this equation 2 as we will likely need it along the way. Next, we're going to resolve horizontally. Okay, so let's resolve horizontally. I hope we've got space. Yes, we do, so it's fine. Right, so resolving horizontally, the forces at play would be the component of T, the horizontal component of T, which is going in this direction to the right. Okay, so essentially that's T sine theta. So we have that T sine of theta and T sine theta. Then the next force is the R force going in an opposite direction to that. Okay, so that's going to be minus R. Okay, so say here minus R. Any other horizontal forces? No. So this is just going to be equal to 0. All right. So this is what we have. So we can actually say here that R is equal to T sine of theta. I'm going to call this equation 3. All right. So we are done with that. Okay. Just going to move this a little, maybe upwards so that we can be economic with our space. Okay. Let's move on. One more thing to consider is the fact that at limiting equilibrium, F is equal to mu R. Okay. F is equal to mu R. So essentially here, we're going to do the third thing. Okay. So number 3 is F is equal to mu R, which is gonna mean that F is actually equal to mu, the coefficient of friction. We've been told that is a half. So F is equal to half of R. Let's just call this number 4. Okay, that's fine. Now, what are we supposed to find? The question says, given that the vertex B is about to slip up the wall, which we've considered, find the value of tan theta. All right. Now, we're going to consider the fact that we have gotten that F is equal to half R. So where there is F, say in equation 2, we are going to put half R. So we're going to take equation 2, which apparently was, okay, equation 2 is what we have right on here. So let's place it down here. So from equation 2, we had W plus F is equal to T cos theta. So I'll say since F is equal to half R, it will be W plus half R is equal to T cos theta. All right. So that's what we're having here. We're also going to consider from equation 3, we have been given that R is equal to T sine theta. So R is equal to T sine theta. So since R is equal to T sine theta, it therefore means that this particular equation that we have can stand out as W plus half of T sine theta being equal to T cos theta. We can actually make W the subject so that we have T cos theta minus a half of T sine theta. Remember, the objective is to eliminate everything like W and T and all that so that we are left with the trig functions. So that's why here I had to make W the subject so that we can figure out a way to eliminate it or substitute it so that it gets done away with. So this is where we stand. W is T cos theta minus a half of T sine theta. This is the same as saying W is equal to T of cos theta minus a half of sine of theta. Okay. Let's also look at what we have. If you look at equation 1, okay, let's take equation 1 as it is. So here we've got equation 1, and equation 1 says T is equal to W of cos theta plus sine theta. All right. So essentially, we can say W is equal to W, okay? The W from this equation, which is, I'm going to put it to the right, T of cos theta minus a half sine theta is equal to the W from here, which should be essentially T over cos theta plus sine theta, all right? So with this equation, we can actually divide both sides by T, goes in once, and multiply both sides by the denominator so that we have 1 being equal to cos theta minus a half sine theta of cos theta plus sine theta. So this is now good for us because we now have only the trig functions in here. And I think we are now well on our way to finding the value of tan theta. Okay. So let's see if we can take this a little bit further. Okay. So if we expand the brackets, okay, here we get cos squared theta. And here we get minus a half of sine theta cos theta. And here we get, that's going to be plus sine theta cos theta. And that's going to be minus a half of sine squared theta. So this is what we have, and it's all equal to 1. So essentially, we have 1 being equal to cos squared theta. And for this part, that's just going to be plus a half of sine theta cos theta, and that's minus a half of sine squared theta. So we can move the 1 to the right. So we are left with 0. So 0 is equal to, and the 1 becomes a minus 1. So we now have cos squared theta plus a half sine theta cos theta minus a half sine squared theta, and it's now minus 1. Okay. And I'd want you to consider cos squared theta minus 1. All right. Where we know that sine squared theta plus cos squared theta is equal to 1. And sine squared theta is 1 minus cos squared theta. And we can also say minus of sine squared theta is equal to cos squared theta minus 1. We're going to use this result for cos squared theta minus 1. So essentially, that's going to give us 0 is equal to minus sine squared theta plus a half sine theta cos theta minus a half sine squared theta. And now minus sine squared theta minus half sine squared theta is actually minus 3 over 2 of sine squared theta, okay, plus a half of sine theta cos theta, okay. So 0 is equal to, I'll factor here a half of sine theta, which will give us minus 3 sine theta plus cos theta. So here it's going to be either a half sine theta equal to 0, okay, or minus 3 sine theta plus cos theta is equal to 0. So we are going to say essentially 3 sine theta is equal to cos theta, and we divide everything by 3 cos theta, this side by 3 cos theta. The 3's cancel out, and we are going to be having tan theta being equal to a third. So the value of tan theta here is a third. That's actually what they want us to find, right? The value of tan theta. So we're getting that tan theta is equal to a third. Okay. So that's how we do it, Wagner. What do you think of this?
Okay, sir. So my question is, the question said it was a rough vertical wall, okay?
Yes.
So even at point B, it's rough, right? So why don't we consider friction also over there?
Yes, the wall is rough, so the contact with B is rough. So that's why we had to put in the friction right at B. Okay, I don't know if I got your question right. Can you maybe say your question again?
So at point B, it was rough, so you put S, right? And also it's a rough vertical wall, so also in point P, it should also be rough. So why don't you add force, frictional force over there
Okay,
also?
so the point P is fixed. If you look at what they say here, it's a fixed point P. It's fixed. So since it's fixed, we're not going to really care about the friction there. But the point B, the contact with B now, is the one that is movable, okay, where friction is going to matter the most. Okay, so that's why we will only consider friction for B, because P is just a fixed point. I hope you understand.
Uh, okay, sir. And my second question is, how do you know the friction acts downwards, not upwards?
All right. It's because of the fact that they told us here that the vertex B is about to slip up the wall. You see this part? They say the vertex B is about to slip up the wall. So if it is about to slip up the wall, it means friction is going to act in an opposite direction to possible
Uh,
motion. Mhm.
okay.
Like
Yes.
that.
And the rest is so and one minute, sir. So for your horizontal components for part two, um, you did P sine theta minus r equals to zero, right?
Yes.
Uh, sir, so what about the W? How do we know it has no horizontal components?
Okay, so when we were resolving the W force is completely vertical. It's a vertical force. It's parallel to the vertical wall. So its horizontal components are going to be zero. So that's why we didn't consider we considered it when we were resolving vertically, but not when we were resolving horizontally.
Mm. Yes, sir, that's it.
All right, that's fine. But I hope you understood the rest.
Yes, sir.